Hey, welcome everybody to day 2 of DNS-OARC. My name is Manu, Bretelle, and I work at Facebook, and I will be sharing the sessions today. I will be with Jake, that is going to be our timekeeper. You may hear his voice like 5 minutes before the Q&A session. Like yesterday, you will have chances to rate the talks. This will happen during the Q&A. Please do so. This helps the speakers and the forum committee to get feedback on the talks. Today, we will start with a series of talks, and then there is a member-only session. You members should have received a link. If you didn't, please send an email to admin@dns-oarc.net. Without further ado, I would like to introduce Ben Schwartz from Google. He's going to tell us about everything about service binding, HTTPS, and SVCB records. Ben?
Hi, thank you, Manu.
Hey.
I think of this talk as really just a warm-up for Ralf Weber's great presentation that's going to immediately follow. So you may have seen these slides before. These are almost identical to the slides that I used to discuss this topic at the RIPE DNS meeting in, I believe, October. They're also pretty similar to a series of presentations that have happened at the IETF. But even if this is old news for you, please stick around for Ralf Weber's talk that's going to follow on a similar related topic.
FYI, we don't see your slides yet. Perfect. We see them now. Thank you.
Great. So I'm one of 3 co-authors of an IETF draft that's approaching finalization that defines 2 new new DNS record types: the service binding type, or service B, and the HTTPS resource record. To tell the story of how we got here, we need to talk about CNAME. I'm sure everybody here knows about CNAME, and CNAME is great. It's really a brilliant component of the DNS system. But it does have this one crucial limitation, that no other data should be present at the same node that is on the same name as a CNAME. And that's because a resolver with a cached CNAME will follow that alias without further communication with the authoritative to see if there's anything else there. So in effect, there cannot be anything other than a CNAME at a name, which means there can't be an NS record at the same name.
Ben, sorry to interrupt. Just to let you know, we don't see your video. I'm not sure this is on purpose or not.
I believe this client only supports screen sharing
Okay.
or video, not both at the same time.
All right, thanks.
So because of this, you can't put a CNAME at a zone apex. Okay, that's background. Another important piece of background is SRV records, which again, I'm sure many of you are familiar with. SRV records, in a sense, solve this problem that CNAMEs can't alias an apex domain. SRVs can sit alongside an NS record at the apex and can provide a kind of indirection where clients will follow an alias to the specified target name. And this is widely used and solves the apex aliasing problem for a lot of protocols, but it is not widely implemented for HTTP in particular, much to the disappointment of some people who would like to solve this kind of problem for HTTP and HTTPS. And it also has suffered from some problems related to a latency penalty, basically problems if intermediate layers of the stack are not aware and supporting of this new record type. SRV is no longer such a new record type. But alas, there still are many components of the DNS system that are not really suited for it. So that was the status quo in 2000. And then over the following decades, we've seen in my view, some transformations of how the internet is used at scale. One of the important things that's changed is that CDNs have emerged, and CDNs make heavy use of CNAME to make it really easy for people to point their domain at a very large scale hosting operator who can handle all the details of web hosting. That's easy and convenient, but it can't handle the apex domain. And so there's a real puzzle about what to do if you really want a CDN to host your apex domain. And I won't talk through all of the details here, except to say that it's inconvenient. It can be done, and it is certainly done at scale today, but it's not as easy as just CNAMing your name to a CDN. Once CDNs became well established, we started to see a growth in interest in multi-CDN hosting. Multi-CDN hosting is particularly important for clients to be able to move between CDNs, because there's always going to be a transition period where some users are experiencing a website or reaching a website on the old CDN, and some users are reaching it on a new CDN. And in order for websites to be able to move cleanly between hosts, it's really valuable if those transitions can happen invisibly without downtime. So again, with CNAMEs, this is relatively easy. The DNS standards don't make this easy to express in a zone file, but you can, in effect, just have two CNAMEs. And everything will basically work fine. And as you roll out the second CNAME, users will flip over to the new CDN. But what about for the apex domain? Well, this is actually relatively straightforward. You can just sort of mix the IPs together if you want to host on two different CDNs, especially, for example, if you want clients to be able to fail over between them if one of them experiences downtime for some reason. And that works fine. The CDNs are completely interchangeable. But in 2018, we saw the first version, the formal version of a proposal for encrypted SNI, which is now called encrypted client hello, which is an addition to the TLS standard. In this addition to TLS, the TLS server publishes a public key in the DNS, and the client fetches it and uses it to encrypt the first message. I suppose I should say that Dane-based authentication operates in a similar fashion. And so if you're using encrypted client hello, or probably also if you're using Dane, CDNs are no longer interchangeable. The client gets a public key for a particular CDN. Trying to use CDN A's public key with CDN B's IP address is going to fail hard. So we have a problem. And the solution is that we need a new record type that allows us to bind together these pieces of information so that the service's IP address and the public keys and whatever else the client needs to know are all bound together into an atomic collection that is not going to get chopped up into pieces and then mismatched by the time it gets to the client. And we also need to allow aliasing the apex, because the CDN, the hosting infrastructure, needs to manage both its IP addresses and its set of public keys. We really don't want to put ourselves in the position of CDN clients copying the CDN's public keys into the client's zone, which is ripe for all kinds of terrible problems, like making it impossible to do key rotation and expiration. So we need a way to bind together all of this information about a service, and we need a way to alias names to that bound collection of information. And so we call this a service binding record. This is the zone file form of the new RR type. It looks a lot like SRV, which is not a coincidence. But it is also substantially different in a few different ways. Like SRV, it has a priority field. That priority field has a special case for priority 0, which means alias. Effectively, it means go to the target name and do another service binding query. Otherwise, the SVCB or service binding record contains an arbitrary key value data store where the keys are IANA controlled. And so this can contain, in effect, a complete description of anything the client might need to know in order to connect to the server. And just like SRV, the client has to chase these aliases, which creates a performance problem. And just like SRV, the recursive resolver can help by doing some additional section processing to include those follow-up responses. This draft also defines a new RR type called HTTPS. And this is exactly the same as service B, except that the naming scheme is defined not to use the underscore prefixes. So if I go back one slide, service B uses an underscore prefix scheme, not quite the same as SRV's, effectively designed to encode the authority portion of a URI. So if you have a URI that has some scheme and a name and maybe a port, or possibly other information, this is flexible depending on the exact protocol that you're trying to indicate, that's all encoded into the name here. With HTTPS, those prefixes are skipped if the protocol is HTTPS, which it always is, and the port is 443. And this has two really important properties. It makes wildcard domains work a lot better. It means that you can put a wildcard HTTPS record next to a wildcard A or quad A record, and everything basically should work. It also means that existing CNAME delegations work. So if a client issues an address query and a service B, which is now an HTTPS query, to the same name, and that name is CNAMEd to some other name, both of those queries will follow the CNAME, and so they'll get you'll get the right information that you're looking for. Whereas if there were prefixes, the client would have to add an additional CNAME, or I guess hypothetically convert the CNAME to a DNAME or something. And since there's an enormous install base of these existing CNAME delegations, we felt it was important to maintain compatibility. Another interesting thing that the HTTPS record does is that it signals that the origin is available over HTTPS. And so the client takes this as a signal to never speak unencrypted HTTP to this endpoint. The client will not be susceptible to SSL stripping once it gets this record. So here are some quick examples. This is an example of alias mode. I'm happy to come back to this if people want to talk about it more. This is an example of service mode where there's some actual information about the service. One important thing that this highlights is that the HTTPS or service B record has the ability to convey that a given endpoint supports HTTP3. And so this is interesting and new. It means that a client, before it connects to an HTTP destination, can find out that this destination supports HTTP3, which runs over UDP, over QUIC, and make use of that in its initial connection. So you can potentially, with these records, have clients that reach you without ever speaking TCP, whereas without this record, clients always need to speak TCP over standard TLS at least once in order to find out that the service supports HTTP3 and follow that upgrade path, which costs many, many round trips. One key thing about the client behavior here is that if the client is a dual stack client that's already issuing A and quad A queries, every time the client issues an A and quad A query, if we're talking about an HTTP web browser-like client, it's also going to issue an HTTPS query. So roughly, we can expect something like a 50% increase in query volume from endpoints of this kind. And Ralf Weber will share with us some information about what kinds of query changes they're currently observing. The client has to follow aliases if the recursive resolver doesn't do it for them through additional section processing. And the client essentially has full responsibility for following all of the indirections here. One of the tricky things here is encrypted client hello. Because encrypted client hello contains security relevant information, the client can't proceed with the connection until the HTTPS record completes. So the client needs to wait and find out if there is our data here, if there is an HTTPS record in the zone, before it can even begin the connection process, really. There's some subtle optimizations there, but that's fundamentally the limitation. And this is a potential operational challenge, given that we're introducing a new RR type. This is just an example of a use case for the multi-CDN case. There's a tricky thing with HTTPS and service B records called IP hints. This has been, I think, somewhat controversial. I mentioned earlier that clients are responsible for chasing the aliases and target names if the recursive resolver doesn't do it for them. The IP hints are a way to reduce the performance cost of that case. So they're only applicable in the case where the recursive resolver is not doing the additional section processing. And they're specified only as hints. So the client is recommended to still follow the alias and cache the address records for the target name so that in future connection attempts, they won't use the hints, they'll use the actual address records. So these resource record types are real. They have assigned code points. The draft is nearly final, and there's serious deployment now in clients, in servers, and now in resolvers. I happen to work at Google, and so I'm happy to announce that Chrome now has real code that is being tested for performing these queries, although not for taking any action with them yet. Right now, we're just testing whether we can actually perform the queries safely without it causing any problems. And I'm happy that Firefox is also doing some experimentation here, and that there are many authoritative DNS implementations that are making great progress here. So that's all I have for slides, and I'm happy to take any questions.
All right, thank you, Ben. Yeah, in terms of questions, please, we have two ways to do it. Either you can type your question in the Q&A tab, and I will ask you a question, or you can raise your hand and ask your question by yourself. We have a question from Hazel Smith that is going to ask you. All right, Hazel, you can unmute yourself.
Hello. So you mentioned that with the HTTPS record that clients will no longer need to perform a TCP connection in order to find out whether they can, for example, use quick or something to the specified endpoint information. How much mind has been paid to considerations around security if a client, for example, receives a HTTPS RR, perhaps in the additional section, and it's not authenticated data, i.e. it's not sort of protected by DNSSEC?
That's a great question. The specification does not rely on DNSSEC. So clients always treat HTTPS records as untrusted, potentially adversarial information. Any adversary who can inject these kinds of records also almost certainly, as in our threat model, I think certainly, has the ability to deny the client access to the address records that they were looking for. So essentially, we view denial of service attacks as out of scope. Our adversary can always deny the user access. But
yeah, I guess I was wondering whether this made any difference to cache poisoning attack or something. If you were to set Q type to HTTPS or something, or SVCB or something, and try and basically get a spoofed record in an intermediate in a resolver sort of thing.
Yeah. So there are essentially two concerns that I am aware of here. One of them is denial of service. The other one is breaking the SNI privacy guarantees around encrypted client hello. So the purpose of encrypted client hello is to enable SNI privacy, where the server name indication in the TLS handshake is not visible in clear text. An adversary on the DNS path here could essentially deny the user access to the encrypted client hello public key, or you can try to imagine, maybe synthesize a different, substitute their own encrypted client hello public key, and thus learn the TLS SNI value. But that adversary already knows the TLS SNI value because it is the Q name.
I mean, assuming it wasn't like star.onmicrosoft.com, or I mean, I suppose that depends on the threat model for the adversary. If the adversary has received the question that the original client sent, then they have the Q name. But if in the cache poisoning attack, where they've just tried to convince Google Public DNS to serve false HTTPS records for star.onmicrosoft.com, for example, they might not know the full Q name that a client will be asking for. If you follow me.
I think I do. That is an interesting threat situation.
I have no idea how practical it is, but
yeah, my instinctual reaction here, I guess, is that we just kind of have to accept that kind of vulnerability. That we essentially don't have another option.
Yeah.
But and of course, we are describing a very powerful adversary there.
Sorry to intervene. I think there is more discussion to this. Maybe it's worth taking offline. A couple of more people would like to ask questions. So for the sake of time, I would like to give other people a chance to ask their question.
Sounds good.
Is this fine, Hazel? All right, thank you. All right, next up is Paul. Paul Muchin, you can unmute yourself.
Sorry, I think it was an accident. I raised my hand.
All right, okay. All right, I guess next up is Wes.
Hi, Ben.
Yeah, thank you.
Excellent presentation, by the way. I think that the logical flow and the needs were all really well spelled out. You did a great job, educating us on why this was needed. The underbar history is kind of interesting because we decided to stop publishing records at the apex of its own because, too much, especially for things like wildcard and stuff like that. But then, now we have this HTTPS record, which gets an exception because it needs wildcards. Isn't this kind of setting a precedence? I mean, should we now allow everybody in other protocols to make use of records at the apex because it's easier for them as well? Or is HTTPS special for some reason, and what makes it unique if that's the case?
I think I'm missing something in your discussion here. What is the rule that you're thinking of? I guess I'm not aware of a restriction that says that we shouldn't put record types at the apex.
Yeah, it's not a rule. It was one of the reasons that the underbar, port and protocol came around was because too many records were getting there with SPF and text and everything else. It got to be bulky, and the IETF community sort of decided to push back against, let's stop pushing stuff there. Let's put it at lower levels using, this newer convention so that we stop putting stuff at the apex. What I worry about is, a lot of people will suddenly go, oh, well, this is no longer necessary. We actually can do the apex records because, HTTPS has now turned that around and set a precedence back the other direction.
That's interesting. My sense of the history there was a little different. And I guess my feeling was that these underscore records, the underscore prefixes are particularly valuable where their contents are parametric in some sense and sort of unbounded. So an example in the case of service binding records is that there's a port number, actually also in the HTTPS record, there's an underscore prefix port number, which obviously we can't encode into an RR type. We can't have an RR type for every port number. So that's the case where underscore prefixes are most easily motivated from my perspective. I also have the impression that there have been changes to the RR type registration procedures over the last 10 or so years that have made it easier to create new RR types. And so whereas underscore prefixes were a way to avoid the overhead of creating a new RR type for new use cases, that overhead has been substantially decreased, in part to try to reduce the ever-growing abuse or creative use of TXT records. All
right, folks. I think there is also a long, quite a fair amount of time that could be spent on that topic. We're going to run out. We're running out of time for the Q&A, so let's move that offline. We can use the chat room in Mattermost. For now, it's time for Ralf from Akamai to tell us on the other side of the HTTPS record as it's seen in production. All right, Ralf, you can share your screen.
I can.
We can see your screen.
Okay, and going into presentation mode. So thanks, Ben, for the very good introduction of what HTTPS is. That's much better than what I could have given. I'm going to just leave it at that. It's the best thing that sliced bread, because that's really what it is when you come from a DNS or web perspective. And I'm not going to, go over here. It is kind of like it was done before with SVC, and we now have service binding. So it is seeing lots of traffic, and we have an implementation in our cache resolver, and we are getting data from ISPs around the world. So we actually see what the implication of this is. And here, this is a graph from one of our ISPs that shows the query load differentiated by RR types. And as you see, most of the stuff is A, then we have a bit more quad A, and then at the bottom here, you see it's going up from mid-September, as you see here, to a significant portion of the traffic that is now HTTPS. And that's really query volume. It doesn't tell you that there was any answering. It's just the client asked for HTTPS records. And when we look around the world, we see some, stuff that makes sense. There's more Apple in sort of APAC, North America, less in Europe and South America. And as Apple is the only implementation, the query loads are different here. And this is, of course, a graph that shows you when there's huge impacts, but when did it actually start? And to look into that, we convert these to a log graph, and then it looks like this. As you see, the first record we actually received was on July 17th that we saw in Asia Pac and Europe. And then you see a couple of dates here. That's when Apple probably did the public beta. That's in August. And then here is the release of iOS 14, and then it goes on for there. So all of this is pretty much expected. So now we know that the volume and when it happened, but did it go wrong? And the first question to ask is, well, what signals wrong for DNS? Because I mean, there are some error codes, NX domain, not imp, serve fail, but out of these, really, only serve fail has gone wrong. And gone wrong here is from sort of the client side. So this is the answer that the resolver gives back to the client. And serve fail is a thing that you normally don't want to give back, because serve fail is something that cannot be cached. So resolvers usually do go a long way to not answer serve fail. But in some cases, they have to. And that means something has gone wrong. And to show that something has gone wrong with HTTPS, I sort of compared the amount of stuff that has gone wrong to the overall amount of stuff for that record type. Because keep in mind, the HTTPS volumes at the beginning were very low. So if we just had absolute values, that wouldn't make sense. But to show you if something goes wrong, we are comparing good to bad answers in the DNS. And the results are here. So as you see in the beginning, stuff went wrong. And then it turned down, which meant probably people were noticing stuff and fixing it. And then there's one spike here. That is the release, the public release, when people said, oh, shoot, something's still wrong, but it was seemingly fixed. And after that, you see the impact of bad HTTPS record really is not high. It's lower than actually quad A in some cases. And again, we look into this regional. Similar there seems to be some more problems initially in Asia Pacific and some weird things in Europe. And the odd thing is, so yesterday I thought, well, why not crunch the latest data from January and add it to this graph? And I did this, so you see the year here, this is the start of the year, and then I saw this. Unfortunately, I didn't have the time to look into it, what went wrong there. But again, it seems to be one event when maybe something came out and it kind of died down quickly after that. So now to how does this wrong answers happen? And the question we have to ask us is, well, what is the correct answer for an authoritative server if you have a new query type? Well, it's simple. There are sort of three options. NX domain if the label does not exist. So, and I just made a simple, so blah.DNS-OARC doesn't exist. So it doesn't exist in HTTPS, it doesn't exist as an A record, and it doesn't exist as a quad A. So the answer is NX domain, period. You give an authority section, so you have the negative caching. No error and an empty or a CNAME in case you are chasing CNAMEs, only answer section. In the case for DNS-OARC, which doesn't have an HTTPS record, well, you give best no error. You have a question section, you have an authority section, so that you know the data is authoritative, but there's no answer. So that means, okay, of course, the best is, well, to answer with an HTTPS resource record. And now we're going to look into, well, how many people do this and what are the results? So overall, the whole world, this is one day, February 1, just the day I choose, but the other days, the earlier days, and I looked into some days after, second was it, yeah. Also, it looks pretty similar. So we see 403 million unique FQDNs on that day. So out of these, 12 million asked HTTPS resource records. And out of these 12 million, only 126,000 had actual HTTPS record. So out of the stuff that is asked, about 1% has HTTPS records. So really not that much. Now I want to do a quick shout out to Geoff and Joe here, because one of the reasons we see so many unique FQDNs is that people are trying to measure stuff with DNS, and they are using kind of unique FQDNs for that. And when I did this research initially, of course, I just kind of replayed a whole bunch of traffic to Geoff and Joao, and I then noted, didn't he talk about that domain once ago? And I asked him, well, is it your domain? So he said, yeah. And then I kind of extracted it. The interesting thing is my initial use case was, well, I'm going to ignore everything that only had a single query, because, I mean, that's just noise. Oddly enough, even in my traffic set, a lot of these stuff that Joff and Joao did had multiple records. So someone was replaying them to our servers somehow. So, but let's look deeper into it. What are the 126,000 records are? Well, bummer. There is 0 resource record that uses the alias feature. And I was really shocked by that. 0, nothing, nada. And I have no idea why, but at the moment, all of them are using the kind of target record. And all of them use kind of priority 1. There's only one domain that uses more than one resource record and uses multiple domain, and that's nextdns.io. What they are doing, I don't know, but that was really the only domain. Out of these 126,912 have no ALPN. That means they don't tell you that you want to connect over H2 or H3. And 67 are HTTP only. Now, the problem I discovered, and I mean, I'm sort of DNS guy, so HTTPS is not kind of my first thing. So when I did some testing for my own benefit and set up some HTTPS records, I set up HTTP servers to see if they were kind of, if the redirection were coming directly. And oddly enough, app implementation reached them. And I then kind of talked to some of the options that, well, that's wrong, because they're supposed to have HTTPS only. So this is something that is currently, but I assume will go away. So keep that in mind. And the other thing that you see, nearly all of them have hints. And well, 17% have IPv4 only hints, which, I mean, means they are pretty prevalent in V6, because that's probably more than we have whole of V6 deployment. There was no use of other keys, no ACH, no ports, no key, whatever. You can have generic, you have generic form like you have for DNS records, use record type in service binding parameters also, but none of that was used. It was really, most of them were pretty much ALPN, H2, and then a target or the dot as the target of the domain name. As you see, the APLN distribution, I mean, there are 3, I mean, H3 was with some flavors, and mostly also included H2. They were really, I mean, the other 2 are, you don't see them here, there were 5 or 7 or something like that. So really not that much. So now we go back to what can go wrong. So this now tells me, well, I collected all of these domains, and I wanted to see where authoritative servers are really failing. Now, keep in mind, this is a single kind of place where I tested this from, so the answers might be different from other places. But I initially kind of, out of the 12 million domains, made a sample, and I said, well, if you answer different for an A record than for an HTTPS record, so you don't have a coherent answers, then this is wrong. I mean, if you answer a serve fail for A, quad A, and HTTPS, you're host, I don't care. And if you answer sort of NX domain for all of these, I also don't care. And I only care about domains where you give a different answer for A and quad A than for HTTPS. And out of these, out of 12 million domains, 168,000 answer sometimes wrong. Now, sometimes wrong, I mean, in the DNS UDP-based stuff fails. So you always have a serve fail rate in your server that something goes wrong for some reason, and some that goes good again and then bad again. So I want to see, well, what is kind of consistent? And to do that, I sort of tried them to our resolver and actually made a log of the whole recursion process. And out of these 160,000, only 4,652 proved really wrong. So there's not that much wrong domains. And the answers that were coming back sometimes were funny, although not funny well. So there were lots of authoritative name servers that answer for nothing but A and quad A. And some are even, I mean, some give answers back for NS, but not for SOA. And there was one server that I just kind of tried. Well, type 65 doesn't work. Well, what about type 60? Well, oh, that does work. Type 61? Oh no. Type 59? Yeah. So all of this stuff happens. And there's also sometimes when you answer NX domain for HTTP, but not for A and quad A, this is very bad, because if you follow RFC 8020, then this means, well, the A and quad A records no longer exist. There are, and I guess others have it also, of course, stuff in the server that says, well, if you ask for A, I'm just going to make sure. Maybe I'll ask again and see if an A record is there. But that is very common, although not so common as the most common is timeout, and then the timeout doesn't matter if there's an X domain at the real A record, at the A record, or at the, and the other is NX domain, no error, and the oddest one is only one, I believe, NX domain and timeout. So these are the error conditions. So that brings me to the summary. So overall, I believe the adoption of HTTPS has been relatively smooth. There initially were problems, which I would expect anything. I mean, there currently is one implementation and a limited feature set usage, Apple, iOS, and macOS. But it is still, I think, a success story, I would say. And of course, the devil is in the detail, and DNS is hard. And to anybody out there who writes authoritative servers, answering is always better than dropping. Query types other than A and quad A's are not attacks, they're regular query types. And answering NX domain when you just don't have the data for the type is wrong. And the last one, I mean, will SVCB ever be used, or will HTTPS take over the world? And that's it. And with that, questions.
All right, thank you, Ralf. A quick reminder that Paul will show up to be able to rate the talk. You can ask your question in the Q&A tab and I will read them out, or you can raise your hand. We got a couple of questions in the Q&A tab. So starting with Peter Alexis, the question is, you said you have an implementation. Does this mean cache serve does the SVCB HTTPS additional lookup?
Absolutely. So there's a thing, I mean, again, we're optimized for speed. So we'll only we'll do the lookup, but if we don't have it in the cache, we'll just give back the answer first. And then the next lookup comes, we'll give it back with the answer in the cache, yes.
All right, thank you. Next question, Hazel Smith. You mentioned that some were answering NX domain for HTTPS and no error for A quad A. Were there any where there were empty non-terminal, meaning qname-example.com returning an NX domain for Q-type HTTPS and returning no error, with empty answer section for A or quad A, where record exists below that name?
To be honest, I haven't checked that. That might be, but yeah, I haven't checked. I'll take a look if I can get something out of the person that I asked.
All right, thank you. And then we got a couple of hands up. All right, Hoffman, you can unmute yourself.
Hi, this is Paul Hoffman from ICANN. So Ralf, thank you very much. Seeing real world stuff for RR types that actually haven't been, that we don't have standards for yet, but we feel like we know what we're doing is really good. I am incredibly intrigued by the thought that there are authoritative servers out there giving, as you call them, wrong answers. And I'm assuming, like you did, that this is a wrong answer because it's a new RR type. Separate from this, did you start looking for patterns, like was that all from one server farm, or did it seem things like that? Because it seems, I'm hoping that it is one implementation that we can then figure out which implementation it is and chase down the vendor as compared to the authoritative server themselves. Did you run that down, or were you mostly focused on the good parts of this, which was the HTTPS?
Well, so I have, but I haven't. I have the server names or that are answering bad, but I didn't look at PDNS and try to figure out what kind of vendor that is. And I'm not sure. Maybe I can. I'll have to ask if I can share the data, but that might be something to further investigate.
All right, thank you. Next up, we got Ben Schwartz. You can unmute yourself, Ben.
Hi. So on slide 15, maybe that's the slide that everybody is interested in. I wanted to clarify, are these only domains that do have A and quad A records? That is, where you didn't get a no data response for A or quad A?
So I guess, but as Hazel asked, I haven't checked. So these were domains that were asked, but I didn't check if they had an A or quad A. The only check I did to get into this pool is someone asked for HTTPS, and the answer that I saw in our data was incoherent. So it was either a serve fail or I didn't check on actually records, but that should be easy to check.
Okay. Do you think that probably most of them are not no data?
I would think that most of them have A records or quad A records.
Okay.
But
what was the, just quickly, what timeout, or roughly what timeout were you using to declare timeout?
We're using the standard cache serve timeout algorithm. And so the thing is that because, keep in mind, a serve fail there means that cache serve has gone to all the servers. Because again, I did use a special function in the server where you can actually trigger the recursion process, and then it will tell you what it does exactly, and it will try really to get an answer. So having a serve fail there really means there was no way to get an answer. So all the servers were bad.
Thanks.
All right, thanks, folks. I don't see anybody else raising their hand, or there is no more question in the Q&A. So with that, I would like to thank the Farsight has been the workshop sponsor, and we will now go for a 15 minutes break. We will resume the session at 17:05 UTC sharp. Thanks, have a refreshment, and see you in a bit. Welcome back, everybody. We're now ready to go for the second part of this session. Please make yourself comfortable. And now we're going to have Luuk, Hendriks, and Willem Toorp from NLNet Lab tell us about the XDPeriments, tinkering with DNS and XDP. Luuk, all yours. We can see your slides. Thanks.
Perfect. You can hear me as well?
Yes, I can. I guess we all can.
Perfect. Thank you, Manu. Yes, so I'm Luuk Hendriks. I'm with NLNet Labs, and Willem and I have been experimenting with DNS and XDP. And in the next 20 minutes, we'd like to present some of our findings there. So, why XDP? I'm sure many of you have heard about these new fancy technologies that allow you to do a lot of stuff in your data plane, right? Programmable networks, programmable data planes, stuff like P4 and also XDP. They offer flexibility without sacrificing performance. And that sounds very nice. So we thought, well, let's see how we can use XDP in a DNS context. And the good thing about XDP is that the only thing you need in order to start using it is a recent Linux kernel. So that's an easy way to start out. And because you run XDP in your Linux kernel, because XDP is code you write yourself and you run it in kernel space, so you can process incoming packets in kernel space. Because you run it there, you can still benefit from having your user space after that. So what that means is you don't have to write XDP code that replaces everything you currently do in user space. So you don't have to write a full-fledged recursive resolver or authoritative name server, but you can do some parts in kernel space and still have your user space after that. So you can augment what you already have running. Again, if you have a recent Linux kernel, you could actually check out the codes that we have on GitHub and start using it right away. We have a couple of examples in that GitHub repository, and in this presentation, we'll start out with how we can do RRL in XDP. So response rate limiting, I'm sure I don't have to explain this to most of you, but just so we're on the same page, with RRL, you can set a certain threshold, X, and whenever the incoming rate of queries exceeds X, so the number of queries from a certain source IP, you make a decision. You either set a TC bit and send it back, or you drop the packet, right? It's a thing we all know and maybe take for granted. But when we look at this slide, we can see some of the requirements that we need for this mitigation technique. Because if you look at queries per second, it means we need to keep state to do this calculation, right? If we say return truncated, it means we do have to alter the packet before we send it back. And we'll see that we can actually do all those things with XDP. So to explain the other abbreviations, before we can explain XDP, we have to explain BPF or eBPF. Most of you will know BPF from your TCP dump filters. It was the simple VM that allowed you to write those filters. eBPF is they say it's the extended BPF, but it's slightly deceiving if you ask me, because it can do far more than just filter packets. With eBPF, you can run your own code in kernel space without rebooting. And XDP is a hook in your network driver. So we can run this BPF code on every incoming packet. And the nice thing is, again, it happens before you hit the network stack. So before a socket buffer is allocated, hence performance. And DNS, just DNS, well, initially I put this in there as a joke, just DNS, how hard can it be? But in this case, as we are aiming at augmenting what we already have, this is, you can interpret this in another way. We're not altering the protocol here, right? Whatever is running in user space expects normal DNS. And that is what we will do. We'll not alter anything on that layer. So writing XDP code and running it in your network driver, how do we decide what should happen to the packet? Well, that's all based on a return code. So what do we return from our little XDP program? So for reference, your classic stack, packet comes in at the NIC, via the driver, it ends up in your network stack, and eventually via a classic eNet or eNet6 socket, it ends up in your application. Now with XDP running in your driver, we can have a couple options here. We can return XDP TX, which means send it out of the NIC this packet came in from. We can also say XDP drop, which means, well, no surprise there, just drop this packet. And these are two quite simple things, but I hope you can imagine that this already allows you to do a lot of heavy lifting, processing, without even touching your user space, right? If you have to set the truncate bits, well, you can do this with the XDP TX command, for example. We don't need anything in user space. Another one is XDP pause, which means, well, we have processed this thing in XDP and we decide we still need something on higher up in the stack and user space. So maybe we alter some things in the packet, but then we still pass it on. So it can end up, in this case, at NSD. There is another option which we'll be not using, which is XDP redirected, send it out of another NIC, and there is a special case where you can use that return code to send the packet to a special socket type. But to use that socket type, you will need to alter what is running in user space. And you might have seen this in a previous OARC presentation in NOT. So one more time, what we're after is we're trying to augment DNS software. We're not altering the software itself. We're adding functionality just before a packet would traverse upwards into the network stack. We're not changing running software in user space. We're not re-implementing an entire resolver or name server in XDP. So how do you go about this? Your workflow, so to say, to get to a running XDP program is you start out writing C code. And you compile this with Clang, target BPF, and then the fun starts, because once you try to load it, this thing called the verifier kicks in. You're trying to run arbitrary code in your kernel, and we, of course, cannot have any kernel panics there, right, on every incoming packet. Well, we'll only happen once, I guess, but so this verifier checks, does your code terminate? Is it not too complex? Those kind of things. And if it has no objections, it will load the code on your interface, and you're done. It's running. Every incoming packet is now processed by your code. No mod probe, no reboots. You don't have to reconfigure anything in user space. That's it. That's how easy this could be. If you want to interact with that running code, you will need something called BPF maps, and we'll look into that in a couple of slides. So specifically for response rate limiting, and we're not going through every line of code that's on GitHub, but the concepts that we need to parse the Ethernet frame, right? That's something that the network stack would do for you, but now we have to do it ourselves. So we have to make sure, are we dealing with UDP inside IP inside Ethernet, and is it actually meant to go to port 53? Well, okay, this might be DNS then. Check if it's correctly formatted DNS in there. And once we know that, we have to do two things. We track the query rate because we want to do response rate limiting, and based on that, we either decide to pass it upwards or maybe drop it or set a truncate bit and send it back. So BPF maps are specific data structures that require specific helper functions to read and write to them. And if you look in the header files, there's a couple of types that you can use. We are using a hash map here. So that basically means that we keep track of the source IP addresses that we see for the incoming queries. And we map those to what we call a bucket. And there we keep track of a start time, a window, and the number of packets, so we can calculate the rate. So with maps, we can have this inter-packet state. And for those of you who have worked with P4, keeping state might be quite cumbersome, but with XDP, it's actually quite doable. Another thing you can do with maps is this configuration from user space. For that, we're using a different map type here, because what we want to do in this example is exclude some prefixes. So perhaps you have paying customers that you don't want to subject to rate limiting. You can store those in a map via their prefix. That's the key here in the type LPM3, longest prefix in range 3. And as a value, we keep a counter of how often we have hit these things. Now, you've loaded your code onto the interface, so response rate limiting is active there. And now you decide you want to add something, another prefix. You can do this. You don't have to reboot. You don't have to recompile or reconfigure. You can do this either using BPF tool. That's a generic tool to populate these maps, or you can use your own custom user space tool. And now that we know all this, I will hand it over to Willem, which will actually demo this to you.
That's right.
I will stop sharing, Willem, and then I hope
I can start sharing my terminal.
Yes, I can see your terminal.
Perfect. So yeah, so I started a virtual machine, which is running a name server. It's at this address. Oh, let's see. That's working. And suppose this machine is your name server and it is being misused by a amplification of reflection amplification attack. And it has quite a bit of load. And you think, well, I saw this presentation at the DNS-OARC of Luuk and Willem, and I would like to try this XDP program to see if I can reduce the load on my name server by dealing with those packets right after they arrive. And so I'm doing this completely from scratch to illustrate that you did not have to anticipate doing this. You know, you install regardless of what software you are running, or without even anticipating that you ever wanted to do this, you can start using XDP to deal with the denial of service attack. So this Git repository, we reference to this in blog posts that I will refer to at the end of this presentation. There's a first blog post which deals with answering DNS packets from XDP, which it has as the example DNS says no. The second blog post deals with augmenting existing DNS server, and it's the RRL example. But because I will use a user space program to add prefixes that should not be subject to response rate limiting, I also have to check out this submodule and compile this library, which is not available in a package, unfortunately. But we are doing it from scratch, so this is part of it. Then let's go to the response rate limiting example. We actually have 3 versions of response rate limiting that we refer to in our blog post. But round 3 is the fully fledged one that has all the features that you would normally see in your regular DNS software. So I will open the C file. And you can see the parameters. You have to configure them here. I have to adapt the number of CPUs, and this virtual machine has only 1. The prefix length, you can configure that, the size of the hash table, and how you want to respond to the response rate limiting. And for the demo's sake, I'm going to respond with the TC bit for every response rate limited answer, and I will also downsize the response rate limiting to 3 queries per second. So let's make this. Now I have to create the VIP maps, the very important prefixes maps. This is the way how we configure the prefixes that will not be subject to response rate limiting. Now I can load the XDP program, and it's actually loaded. You can see the XDP generic is on the interface. Now let's do this query again that I just did. Good. And also I have to specify the ignore flag so that DIG will not return over TCP when it receives a packet with the TC bit set. Okay.
Gentlemen, sorry to interrupt. There are 5 minutes remaining before Q&A.
Yeah. So I sent a query twice a second, which should not be a problem because we have set the response rate limiting to 3 queries per second. So if I now sleep a bit less, we see that a lot of responses now have the TC bit set. Those will not have the address returned, and only 3 responses per second get answered. So the user space program is this one. Okay, let me first check what my IP address is. Okay, it's this one. So I start the queries again, and then I use this tool to add this prefix. And you see that now all the responses are returned without the truncated bit. Okay, it's the demo. Now I'm going to share another screen. So what have we learned? We can leverage XDP to augment DNS services, regardless of the software that was running the service, to deal with incoming packets. So stuff like access control, or dealing with the service attacks. You can decide to deploy it at any time. You did not have to anticipate it beforehand. BPF maps can be used to maintain some internal state, like for rate calculations, but can also be used to communicate and configure the module from the user space at runtime. So we've been adding prefixes of well-known customers that should not be subject to response rate limiting manually, but there's also a mechanism to do this automatically within the DNS protocol, and this is called DNS cookies. So DNS cookies work together. If you have a valid cookie, you're not subject to response rate limiting. So if you do response rate limiting in XDP, you also have to do cookies in XDP. And this is perfectly possible. There's actually a mechanism in XDP to chain existing XDP programs. So we can, we will be writing about this in the next blog post, how to verify cookies, and if they are valid, pass the packet on to the DNS service, and if not, send it to the response rate limiting program. But that's just for verification. You can also, with BPF, do the creation of DNS cookies. So change or respond on incoming packets and change outgoing packets by running 2 BPF programs, one on the TC layer and one on the XDP layer. But we will also talk about this in the upcoming blog post. So a lot is possible. XDP and eBPF are a very good fit for plain old UDP-based DNS. Less suitable for TCP-based DNS and probably impossible for dot and DO. And we think using XDP to augment an existing DNS service is an exciting new idea and a great new tool in the DNS Operates toolbox. We have lots of new ideas or ideas for to do with XDP and DNS to have more tools in this toolbox. There are examples of some of those ideas, and I think it's now 5 minutes until for you to ask questions.
Yeah, thank you, Willem, and thank you, Luuk. Yeah, this is the time now for people to be able to answer the poll and also ask the question through the Q&A tab or raise their hand. For lack of question at the moment, I had one actually. So I think I'm pretty lucky where I work at, where a lot of the heavy lifting has been done. But are there any resources or any pro tips that you will recommend for people that start playing around with XDP?
Well, you actually don't need that many tools. It's just a Clang compiler and IP route 2 and BPF tool, which already gets you quite far.
All right. Yeah, I think I was also maybe referring about certain resources, documentation that help you bootstrap to bootstrap you.
Okay. Yeah. Well, you could have a look at our blog posts, of course, and also there's XDP tutorial, which we have been using quite a bit to get started with this stuff.
Cool. All right, we got a couple of questions coming up, so let's switch to that. Jeff Westhead has a question, which is, could you talk about performance a bit? How many PPS can these drop and keep the server alive for unfiltered sources?
How many QPS can it drop? So I don't know. So we will start experimenting with hardware offloading of XDP programs, and then it is supposed to be line speed. But it will, at least I can tell you for sure that it will be faster than when running from a user space DNS service.
Yeah, I will add to that. As you said, in the hardware mode, essentially all the processing will be done without even touching the kernel.
Right.
So yeah, you can get line rate.
Yeah.
Next question, which is more of a comment from Vicky Risk. I don't have a question, but I love this, and I want to give Willem an award for his live demo.
Thank you. Yeah. Also, I want also to mention that we have this XDP and BPF channel created in the MetaMost. So it might be interesting for people if they have suggestions or ideas to post that in the channel.
Yeah, good idea. All right. We got our last question that's Peter Alexis is going to ask. Peter, you can unmute yourself.
All right. So it's actually not a question, but a comment. So we have eBPF and DNS dist as well. And we have indeed seen that if you put BPF in the kernel, you can just drop packets at line rate, which is amazing. So this is definitely faster than just doing it in user space.
All right, perfect. Thanks, Luuk and Willem, and people for asking question. We are right on time to go on for the next talk. Let me oops. All right, so next up is going to be Robert Mortimer, that is going to talk about the state of DNS security record. Robert?
You currently stopped my video, so that may be interesting.
All right, yeah, we don't see it at the moment. Matt, maybe. Oh, We can see it now.
Cool.
Perfect. Thank you.
So yeah, I'm Mortimer Nominate. I'm going to talk about the state of DNS security records. Thank you.
We can see you, we can hear you.
Brilliant. So this started as a personal project a few years back when I was deploying SPF and DMARC records and thought it'd be fun to start checking what the vendors I was dealing with were doing. So being lazy, I wrote a tool to just look things up at random as I was being curious. And having written a tool, I started checking more records, checking the things that I recommended best practice by the likes of NCSC to see what was out there. And of course, once you've got a tool and a set of record types to check, the obvious thing to do is start recording the data and make a graph and see how things change over time. So the first time I did that was back in 2017. But the problem was, what was your data source? I started with the Alexa top 100, the list of ICANN accredited registrars, the top 100 registrars. There's a public list of security 500 vendors, which were all good public sources. And I had a bunch of stuff that I was using, so my vendors, DNS providers, anything else I thought was interesting. But that's not ideal. I didn't want to use private data, and there's not that much good public lists out there. So I dumped the vendors and DNS providers and discovered Tranco, which is a great list for this sort of research. Started looking at the OH providers because they're interesting. And as I'd automated this, I then started checking all of the infrastructure domains for those lists. So anything providing MX services, DNS services, anything like that. So starting to be a decent list and all stuff that people can use. I'm probably next year going to drop Alexa because it's just too painful to scrape, and Tranco's a lot easier, but I kept it in for the moment for consistency. So what was the method? I did a lot of DNS records, lookups, really simple, big list of domains, look up all of the records and shove them into a log file that I can then parse and see how those records compared to the best practice document. Was the CAA and SPF and so forth. DKIM records were tricky because I didn't know what the identifier was. But a lot of the time, if there wasn't a wildcard record, you can infer if the DKIM record's there based on whether you get a no error or an NX domain. It's not perfect, but it seems to validate reasonably, and it's the best option I've got. Ideally, I want to check registry settings, see if the registrar locked or registry locked, but who is API access costs money, and this was a personal project. So that's the background. This is what the results look like. And apart from SPF, really, very few of these record types are widely deployed in the wild. And it's been getting somewhat worse, but that might be due to my sampling, which has obviously changed over the years. And the number of ICANN registrars from my list, for instance, collapsed massively between 2017 and 2019. Not sure why, but it changes the sample size. But as you can see, apart from DMARC, everything in terms of deployment has gone downhill. And most of these aren't new, apart from CAA, which we can let off. These stats compare reasonably well with a similar report that CSC do on the Forbes 2000. And the DNS sec is similar to what statsdns.com are reporting across all the TLDs. So I've got some confidence in this. Obviously, a bigger data set would be better, but so to look at how it breaks down, I'm sorry this graph is tiny, but this is the various lists I was looking at. So Alexa, DOH, ICANN, top 100 registers, and so forth. IPv6 isn't security related, but it's just interesting. Most commonly used amongst the DOH providers, which isn't surprising. That tends to be people that are looking at doing some quite cool stuff. And they're also way ahead in terms of DNSSEC, which is good given the service they're providing. And likewise, the CAA uptake in DOH is really quite reassuring, though very low given it's a HTTPS dependent service and very new. I'd have hoped that would have been better. Mail stuff is quite healthy, but for most of the ICANN and the registrars, it's oddly low given that so many DNS services are modified and managed via email confirmations. You know, you transfer a domain, it's an email. And most of those haven't got SPF, haven't got DKIM, haven't got DMARC, which is, I think, a big gap in that security model. It worries me. But some new stuff, and this I think Ben and Ralf may find interesting. HTTPS SVCB this year has got more uptake than Dane, even though Dane's been around for quite a bit longer. This, from what I looked up, seemed to be mainly due to Cloudflare. Most of the people with these records published were on Cloudflare. Dane remains reasonably painful to apply, especially if you're doing rapid certificate cycling, such as via Let's Encrypt. And in slightly depressing news, a couple of ICANN registrars and one of the Alexa top 50 has an Apex CNAME record, even though, as we heard earlier, that doesn't work. This does indicate to me, at least, that the uptake of this sort of security record is really very dependent upon vendor support, and that domain registrars can have a huge impact in the uptake by just changing default behavior. So, a few conclusions. As you probably gathered, I think the uptake's poor. And I think this is partly because there's not many best practices documents, and there aren't many tools to make it easy to adopt these records. There aren't many cheap DKIM reporting services. Changing the default contents of a zone. When you register a domain, if that was DNSSEC enabled by default, negative SPF, and that sort of thing will make a huge difference. So there's a lot as registrars can be done. And there needs to be more research. My personal project's okay, but it'd be really nice if there are other people looking at this and people who've got data sets that are larger, and apparently a lot of the cases, obviously they can't make them public, having something like this to improve the coverage. People reassure me DNSSEC about to take off, and a lot of these things will improve next year. But having heard that for many years about IPv6, I'm not holding my breath. So a very quick sort of overview of where we are with a lot of these DNSSEC records. I forgot to create an any questions slide. So any questions?
Thank you, Robert. There is no question from the room yet at this moment. I have one. When you look at the top 50 or so, over time, are they the same, like the one in 2017, 2019? So when we see regression in terms of adoption, is this from the same set of domains, or the top 50s are just different over years?
So the very top part of the top 50 tends to be static. As you go further down, there's more change. And I did think about that. I do have all of the data sets going back year on year, so I can do a direct comparison, but some of those cease to exist. And in terms of impact for the internet, you know, if something's just become irrelevant, it's great to have adopted something, but it doesn't have that much impact. So looking long term, I thought it more useful to keep what's the top 50 doing rather than a specific set of domains.
Cool, thanks. I guess I forgot to say something quickly before asking the question, was that there were going to be the poll and you can raise your hand or ask the question on the Q&A tab. I see through other mechanisms that Ulrich wants to raise his hand. Let me try. Ulrich, can you unmute yourself?
Yes. Thank you. Raising my hand seems to be much harder than that. Yeah, thank you. A great presentation. We actually do this kind of measurement for the .se zone, and there's a few other zones that are actually public that you could do this measurement on for, you know, larger data set. And I know that there's a group. There was a presentation at the last IMC about this, the group at the University of Grenoble that does this. And I would really like to work with you on this, on the data sets, because I think that is really interesting and could help us to improve security in the DNS a lot.
That would be brilliant. If anybody wants to reach out to me to share data sets and make this a wider ranging survey or see what I've been doing in more detail, be really interested to do that, because I think the bigger coverage we get, the better the data is and the more useful it will be.
Oh, sorry, I'm muting myself. So Sebastian, you can unmute yourself now. Sebastian, did you have a question? All right, Sebastian Castro. All right, I suppose this was not Italian then. Okay, there is no more question in the queue, so I guess we are going to move on to a question from Pallavi. Another angle to this research could be to see data to determine how many queries are made for DMARC, DKIM, SPF by email provider and get an X domain.
So could you repeat that?
Another angle to this research could be to see data to determine how many queries are made for DMARC, DKIM, or SPF by email providers and get an X domain.
Yeah, certainly. And again, if anyone's got such a data set that they can share or wants to see what I'm doing, type their own data set, that would be great. I don't have access to such a data set.
All right, Sebastian is having issue with his mic, so I guess.
Like,
can you try? Oh, I can hear you now.
Oh, okay, perfect. Excellent. Hi, Robert and Ulrich and everyone. So Ulrich was, I think, was talking about the OpenIntel dataset from the Dutch. I also like to point out we're doing this for the .NZ zone, so we have statistics for DMARC and CAA and SPF, and we have an open dataset available if you want to go and check sort of the adoption numbers in .NZ if you want to compare for a future presentation, Robert, just in case you are interested.
That'd be lovely.
All right, cool. Well, we are getting close to the end of the Q&A time period. So I guess without further ado, we're going to move on to our next talk and last talk of the session, which is Paul Hoffman, who's going to talk about a not so popular way of sampling domain names. Paul?
Yep, hi.
It's all yours.
Okay, let me do this screen sharing. And I hate this part of trying to find the right one. There we go. Put it at the bottom of the list.
All right, we can see your screen now.
Okay. Let me just get rid of that. Okay. So thank you, Robert, because you were talking about data sets, and we are about to talk about another data set. Robert mostly covered, like as he said, Alexa's a problem and stuff, and he was covering popular ones. This is a talk about a data set that are not so popular. So, oops, and why? Oh, excuse me. There we go. So my motivation for creating this data set was that, like in Robert's case and in other cases like Sebastian had brought up, you want to know something about the authoritative servers. Are they doing certain things? Or, do they have certain records and such like that? So, the internet has become the web plus DNS, of course. But because the internet has become the web, most people are looking for names of web servers. That's not always the case because, in fact, there's not really a good reason, for example, to have a DMARC record for a name that is only a web server. You don't need a DMARC record for www.example.com. But if what you're trying to do is collect domain names for web servers, that's pretty easy. That's the way we do a lot of research. That's how Robert just did his, and a lot of people. One of the problems that we always have, though, is that when people read our research, is they expect this to be true. What we're saying is to be true for typical domain names. And the way that we often are doing it, like what Robert did, was the most popular websites plus a couple of others that he found, or extracts from zone files for GTLDs, or as Sebastian brought up, or for CCTLDs. I'm sorry, and Ulrich did as well. So these are not typical, though, because, for example, these zone files are full of records that are just used for parking, that they aren't actually active. And the most popular websites, well, there's a zillion websites that we care about that aren't popular, that would be more typical. And the other way that people have done some of this is to get dumps from passive DNS collection systems. But those are sort of difficult to use as well because they're very geographically based. Even if it's a wide spread of passive DNS collectors, it still has large pockets of geography in it. So my motivation here was, in fact, let's look for a base that would have a lot of URLs in it that aren't so popular. And it turns out that Wikipedia pages, for those of you who spend your evenings or even an occasional evening trolling through Wikipedia, you can see that as you go down the Wikipedia rabbit hole, you can end up on a page that lists all of the governments of the small cities in a particular region. So that's a zillion websites that you probably would not see in any of the previous that we listed. Colleges and universities all have a website that generally has been put on some Wikipedia page somewhere. Obscure sports teams. For me, every sports team is obscure, but things like this, music and movie studios, personal sites for academics, that have their own name in them, such like that. So Wikipedia is a wonderful source of this. The other nice thing is that Wikipedia has worldwide coverage. There are Wikipedias in basically all of the languages of the world. The languages often map onto geographies, but onto wide geographies. So for example, the English Wikipedia, which many people use, covers much more than just the United States and Britain. The Spanish Wikipedia covers much more than just Spain and some of the other countries. So Wikipedia is wonderful for this, that if you look at across all of the Wikipedias, you get pretty much worldwide coverage. So here's how I did it. I retrieved the, I'm sorry, I didn't mention one thing. Wikipedia actually makes it easy. You don't have to scrape Wikipedia pages. They have a site for backing up Wikipedia, and that's not just all of the pages. They actually extract some things, and one of those is all of these external links. So there's a database for external links for each language on the mirror of the main Wikipedia site. So I grab all of those, I go through those. It's a MySQL dump, which is painful to work with, but oh well. I extract all of the external links. I clean up the list of the links and limit them to HTTP and HTTPS. As it turns out, that's like 98% of the links on Wikipedia pages, but you find Gopher URLs, you find other things. So I pulled out those. And then so for each of those remaining URLs, I stripped off the scheme because I don't really care for what I'm doing, whether that link started with HTTP or HTTPS. And I strip off everything after the domain name because I'm not looking at these as URLs. I'm looking at them for domain name. This is DNS-OARC. And of course, there's a lot of repetition there. That's fine. I just ran it through unique. And then so here's the data set that I ended up with. So there were about 750 databases that I used from January 1st of this year. They update these twice a month. But so about 750 Wikipedia languages. So after doing the culling that I described there, about 7.35 million unique domain names. Pretty good. It's a large set. If you look through them, they look pretty legit. Like I say, there's a lot of things that you sort of recognize as that's an obscure university in a country that I will probably never visit and such like that. I didn't do my analysis on all 7.35 million because doing queries for 7.35 million things won't tell you much more than doing a sample of 100,000. So I just took a sample of 100,000. I actually had to start with more than 100,000 because it turns out Wikipedia doesn't clean up its data that much, which is fine. I mean, it's a wonderful thing, not dumping on them at all. So I started with 150,000 and figured out which of those actually had IPv4 addresses. So this is my last slide. Of those, and going back to like Robert's thing, about 17% of those names also had IPv6 addresses, which sort of matched visually what Robert did on his slide. And also sort of, that seems what we're doing. Of these, only 4% had, were DNS-SEC signed. So for the people who are saying, oh yes, this is the year of DNS-SEC, DNS-SEC is well behind IPv6. Interestingly, Robert also talked about the Tranco data set, which is a collection of the most popular ones. I took Tranco, I did the same thing, mostly to compare, what are the not so popular websites with most popular. And the number was for V6 was almost identical at 17%. Interestingly, looking at the most popular data sets at a sample of them, only 2% were signed with DNS-SEC, which makes a little bit of sense that those most popular sites probably are more heavily managed, and those people have done the risk analysis. But yeah, so even among that, looking at most popular versus this set, you see some interesting differences. The main reason I actually started this research was some of you who are on the DPRIVE working group remember from the interim in November, I think it was November, maybe December, where we're talking about doing opportunistic recursive to authoritative, and people said, well, if you're going to be probing, it would be good to know how long TLS startup happens. So that's really why I did this. Anyways, all of this will be in a document that's coming out in the future. Here it says hopefully within a few months. It's actually moving ahead a little bit better than I thought. Maybe by the end of this month we'll have it. That has much more detail, since I only had 10 minutes to give this, and talks more about the Tranco. And it also talks about why, even though this is much more typical than the databases we have, major faults in it. And so, for example, even though Wikipedia has many of those things that I listed before, it doesn't have local restaurants, local hardware stores, things like that, which we know have websites, we care about that, but we don't have a way of necessarily getting those into the big thing. So that's it. And I think I hit the right time. Definitely up for questions if you have them.
Yeah, thanks, Paul. So again, please use the Q&A tab or raise your hand to ask questions, and you're going to have the poll popping up pretty soon, which will be your chance to rate the talk. We have a couple of questions in the Q&A tab, so I'm going to start with the first one. Question from Giovanni Mora. Paul, during your filtering, you considered only second-level domain or FQDNs also?
No, fully FQDNs, which was interesting when I had to compare it to Tranco, because Tranco actually strips off www. So I did some changing on that when I did that analysis. But no, one of the things that we've discovered when you look at less popular data sets is there's often a third and a fourth level, like at a college, you know, department.college.edu.country and such like that.
Thank you. Next up, question from Thomas Krizek. Is the domain list you extracted available anywhere, or perhaps the script that were used for processing the raw Wikipedia data?
If you want to read my ugly Python code, I'm happy to send that to you. But pretty much, it's not that interesting. It does the 5 steps that I gave on the slide, but yeah, I could share that. I'd rather not share the database for 2 reasons. One is Wikipedia has a very easy to use license. And so I think people should be doing their own. And also it's for January. It will change over time and such like that. It was pretty easy to run. I think it took a few hours, and I wasn't even using very big VMs for it and stuff like that. So I'm happy to share my code, but I haven't made it that palatable yet. I guess I should add comments and stuff like that. Let me know. Just let me know offline, and I can send it to you. It's a couple scripts.
Cool. Next up, Wes is going to ask his question. You can unmute yourself, Wes, please.
Yeah, thanks. Hey, Paul, I love the idea of doing that kind of search. One of the things that I've been looking at is splitting things across the public suffix list breakpoints to see what the number of prefixes are compared to the base registered domain. Did you try doing that at all to see if there's much variation in prefix use?
I did not, mostly because the measurements that I was getting were mostly about what are typical servers, not where do they live in the hierarchy. So there are plenty of other research questions, such as ignoring .com and .net, for example. So of the .org names that I have, how does that map to the .org zone file? Which might tell us things like how many things in the .org zone file really are just parked. So there's plenty we can do. I haven't looked. This was really, again, my motivation was for deprive, but while I was doing it, I could figure out about the easy questions of V6 and DNS-SEC adoption.
All right, thank you. There is a few comments on the Q&A tab that I'm going to read through. So Hazel Smith says, I too will be interested in the code redomains regarding domains. You'll even have 5-level ones like www.cs.le.ac.uk. Giovanni Mora says, it would be nice to compare Wikipedia versus Cisco's Umbrella, which is also FQDN based. And
Cisco's, Giovanni, Cisco's Umbrella, I thought was actually taken from a set of resolvers. Is that? Which would be a very different sort of thing.
Giovanni, do you want to maybe answer verbally?
Or I could be misunderstanding their database.
Oh, it says true.
Okay, so yeah, so that might be an interesting thing to do, is to compare things that one finds, a database that one finds by looking at the web versus a database that one finds by looking at resolvers.
All right. And final comment from Hazel Smith. Let me know if you will be interested in making this work with PostgreSQL. You mentioned this other word due to MySQL. I sent you a PM on Mattermost about that. Okay. I guess we are right on time. So let me wrap up here. I would like to thank all the speakers and all the people attending and asking questions on behalf of the program committee and OARC. And for now, I'm going to hand it over to Keith, that is going to wrap up the session. Keith?
Okay, thank you, Manu. Appreciate you chairing things this morning. I think that went really very well. So just a few wrap-up things. We're very nearly at the end of OARC 34, another one under the belt. I want to remind all the OARC members that we are doing a member-only session in half an hour. If you register for OARC 34 or you explicitly requested it as a member, then you should have received an additional private Zoom invite. We had a few people who went into the spam folder, so please check that you've got that. And you know, so much for Zoom's email reputation. Please check that you got it, or shout as soon as possible. And that will start at 18:30 UTC for half an hour with Giovanni from SIDN presenting some vulnerability information. We will be switching the remote participation on Mattermost from you're currently in doing that in the workshops channel in the community group. We will be switching to the Town Square channel in the members group. So if you could please make that switch when you switch your Zoom as well. And a reminder to you all that, you know, OARC creates a trusted community. That's because all of your member organizations signed a participation agreement. This presentation is regarded as confidential information, so there are restrictions attached to the redistribution of that as part of responsible security vulnerability disclosure. Looks like the Zoom poll stuff has worked well, so thank you all for giving us feedback on that. You know, we will crunch that data and send it back to the program committee to guide the selection for future workshops. General event feedback is welcome, including feedback on the feedback mechanism. There's the URL bit.ly/OARC34-survey. So again, we'd like to hear your thoughts on meeting logistics and anything that worked or didn't work for you or suggestions. Quick reminder of the next workshops. OARC 35 will be the same format as this one. We're going for the 6th and 7th of May, 1.5 to 2 days long, depending on how much content we got. We got a good pile of content this time round. The CFP for OARC 35 is now open, so please go ahead and submit. Oh, I'm sorry, I failed to share my screen. Friday afternoons. Okay, can people see my screen now?
Yes, we can.
Okay, I apologize for that. There's always something. I'll just recap the relevant slides. Okay, so I was talking about OARC 35. That will be in May. The CFP is now open. There's the URL for the event. On Indico, program committee would love to have your submissions. We will not be doing any physical workshops during January, September this year. We will have some provisional plans for the final quarter of the year, which may include a short online event and hybrid and/or physical events, depending on how the pandemic situation pans out. So the final thing is just to thank everybody. Special thank you to Farsight Security for sponsoring the event, to all the network members and supporters who actively support and engage us, to all the bodies that have awarded us grant funding over the past year. Again, that's really helped us operate things. The program committee, including all our new program committees and new program committee chair, who I think you'll agree have done a great job this time round. All of our speakers. Please consider supporting our online events via sponsorship or patronage for the year, or we will happily accept donations. So that basically, a big thank you. We can all do a round of applause, but nobody will hear because it's Zoom. But thank you to everybody who makes this possible. and especially to the OARC team. Matt and Dinesh have worked especially hard for this event. That is all I have to say for now. See you either in half an hour if you're a member, or at OARC 35 in May if you're not. And if you're not and you want to become a member, please speak to Sue. I'll be happy to sign you up. Okay, thank you.